learn about CPU scheduling algorithms. As we know from last class that we have categorized all the CPU scheduling algorithms into two types, preemptive and non-preemptive algorithms. Now let us learn non-preemptive scheduling algorithms. Here in non-preemptive CPU scheduling algorithms, once the CPU is allocated to a process, the process keeps on doing the task until the process by itself releases the CPU, either by terminating, that is by completing the task, or by switching to do some IO or some interrupt work, that is by switching to waiting state. This scheduling method is used by the Microsoft Windows operating system and Apple Macintosh operating system. Whereas non-preemptive scheduling algorithms are used by Unix operating system. The non-preemptive CPU scheduling algorithm is the only method that can be used on certain hardware platforms because it does not require the special hardware which is needed for preemptive scheduling like the timer. Also, we know that among CPU scheduling criteria, while comparing the CPU scheduling algorithms, like which one is best, which one is worst, so like that while comparing, we have to keep in mind that the algorithm which maximizes CPU utilization and throughput and minimizes turnaround time, waiting time and response time is the best CPU scheduling algorithm. Now let us learn about non-preemptive algorithms. Before going directly to non-preemptive algorithms, first brush up about CPU burst and IO burst cycles. See, as we know, when process starts execution, it will consist of a cycles of CPU execution and also IO operations. So when it is going to do some IO operations or some interrupt service, then the process will enter wait state. So process will be alternatively between these two states, CPU execution and IO wait. Process execution begins with CPU burst. Then it will be followed by IO burst and a combination of these two. Eventually, the final CPU burst, it ends with a system request to terminate the execution of the process. The non-preemptive CPU scheduling algorithms are first come first serve scheduling, shortest job first, priority scheduling and round robin scheduling. Now let us take up first come first serve scheduling algorithm. This is the simplest algorithm and it resembles the normal queue operation. That is, suppose there are certain persons who will be standing in a queue, then how the people are served? Like the first one will get the first service, the one at the end will get the last service. In the same way, here in this first come first serve scheduling algorithm, the process that requests the CPU first will be allocated the CPU first. So it is the first in first out queue format. So when a process enters the ready queue, its process control block, that is PCB, is linked into the tail of the queue, where when the CPU is free, it is allocated to the process at the head of the queue. The running process is then removed from the queue. The code for first come first serve scheduling is simple to write and understand. And also here the average waiting time is long. So in order to illustrate first come first serve CPU scheduling algorithm, Let us consider the example wherein we have three processes with different CPU burst time required by each process, and here the CPU burst time is calculated in terms of milliseconds. Now let us study an example for first come first serve CPU scheduling algorithm. Say, assume at time 0, let the processes that enter the system may be P1, P2, P3, say in this order. These processes are entering the system and they are requiring the CPU burst time, which we are calculating in milliseconds. And assume that P1 requires 24 milliseconds, P2 requires 3 milliseconds of CPU, and P3 requires 3 milliseconds of CPU. Now, when we are using first come first serve CPU scheduling algorithm, if we illustrate it using Gantt chart, then from time 0 to time 24, process P1 will be executed, and at time 24 P1 execution will be terminated. Next, CPU will take up P2, which has already entered the system. Now P2 requires 3 milliseconds of CPU time, so 24 plus 3, so till 27th millisecond P2 will be processed. Next, CPU will be released and given to P3. So P3 will be served at the end, which will be served for next 3 milliseconds, so 27 plus 3. So at 30th millisecond, the execution of all these three processes will be completed. Now, if we calculate the waiting time of each process individually, waiting time for P1 will be 0. Why means, as and when it enters the system, it has been taken for execution. Whereas the waiting time for P2 is 24. Why? Since it waits till the completion of the execution of P1. Then what is the waiting time for P3? It is 27. Meaning P3 should wait till the completion of the execution of P1 as well as P2. So when we take the average of these, average waiting time is nothing but the sum of these things divided by 3. And it comes out to be 17 milliseconds. Okay. So in first come first serve algorithm, for this type of occurrence of the processes, the average waiting time is 70 milliseconds. Now let us assume that P2 has entered first, then P3, and at the end P1 has entered. Why we have taken P1 at the end is that it takes long CPU time. Now P2 is taking only 3 milliseconds, P3 is taking 3 milliseconds, and P1 is taking 24 milliseconds. So now, since P2 has entered the system first, CPU will be allocated to it So for P2, waiting time is 0. For P3, after completion of P2, P3 is taken up. For P3, the waiting time will be 3. Whereas for P1, the waiting time will be 6, which is nothing but the process time of P2 and P3. So after completing P3, P1 is taken up. Here the average waiting time is reduced to 6 plus 0 plus 3 divided by 3, which is 3 milliseconds. So when we compare the first case and the second case, we will come to know that if in this first come first serve CPU scheduling algorithm, if we take up the short CPU burst time process first, then the average waiting time automatically reduces. The next non-preemptive CPU scheduling algorithm is shortest job first scheduling algorithm. So here we compare the CPU burst time of all the processes which are in the system at that particular time, and among them we pick the one with the shortest CPU burst time, and for that processor will be allocated. So here the shortest job will be executed first, and among other processes which are in the ready queue, again comparison of the CPU burst time of all these waiting processes is taken up. Among them, the next shortest one will be selected, and for that CPU will be allocated. Say for example, to study this shortest job first scheduling algorithm, assume that we have 4 processes which are entering the system with the given CPU burst time required by each process. Say P1 requiring 6 burst time, P2 requiring 8 milliseconds, P3 requiring 7 milliseconds, P4 3 milliseconds. So here, even though they have entered the system one by one, P1, next P2, P3, P4, we are not serving them in their order of appearance in the system. We will compare the CPU burst time of all these 4 processes, and we will take up the shortest one first. So when we are doing this, we know P4 is having the least CPU burst time. So first we are allocating CPU to P4 process. Then what next? The remaining are P1, P2, P3 with the CPU burst time 6, 8, 7. Among P1, P2, P3 processes, the least CPU burst time is 3 required by P1. So now we are allocating CPU to P1. Next is P3, which is requiring 7 CPU burst time. So after the completion of P1, CPU is allocated to P3. Then at the end we are allocating P2, which is having 8 milliseconds. Now in this algorithm, so when we are calculating the average waiting time of serving these 4 processes using shortest job first CPU scheduling algorithm, we get the waiting time for P1 as 3, for P2 the waiting time is 18, then for P3 the waiting time is 9, whereas for P4, since it has been served first, the waiting time is 0, meaning it is not spending time waiting for the CPU to be allocated to it. So when we take the average of these 4 processors waiting time, it comes out to be 7 milliseconds, which is less compared to the first come first serve scheduling algorithm implementation. Now let us learn an example for shortest job first, SJF CPU scheduling algorithm. So here assume that the processes, for our example we have taken 4, P1, P2, P3, P4, all have entered at the same time to the system, and the CPU burst time required by each process is, let us say, 6, 8, 7, 3. So here the CPU burst time of all these processes are compared, and the smallest one is chosen first. For the process of this scheduling algorithm, among these 4, P4 is the least one, which has the short CPU burst time. So P4 will be executed first. Then among the rest processes which has the shortest CPU burst time, it is P1. So P1 will be served next. So when it will be completed? 3 plus 6. So at 9th millisecond, the execution of P1 will be completed. Then among the remaining P2 and P3 processes, we have P3 as the shortest one. So next it will take up P3, 9 plus 7. So at 16th millisecond, completion of P3 is done. Next, the left out is P2. So it is served and it needs 8 CPU burst time. So 16 plus 8. So at 24th millisecond, the execution of P2 will be completed. Now find out the waiting time. Okay, waiting time, if we calculate for P1, how much? See, P1 is executed after P4. So till the 3rd millisecond it should wait. So 3. What is the waiting time for P2? Till 16 it should wait. So for P2 it is 16. For P3 what is the waiting time? It is 9. Then for P4 there is no waiting time since it is served first. So the sum, then divide it by 4 to get the average waiting time. Which is 28 by 4. So it comes out to be 7 milliseconds. So here you will come to know that moving a short process before the long one, meaning the process which requires the more CPU time will be attended at the end, and the one with the short CPU burst time is attended first. So when we do that, the waiting time of the short process will be less, and the long process will wait for more time. That is, the waiting time for the long process is increased, but overall the average waiting time will decrease. The real difficulty here in this shortest job first algorithm is knowing the length of the next CPU request. For long-term scheduler, that is for the job scheduler, we can use the length of the process time limit that a user specifies when he is submitting the job. Like when he is giving a job, saying it will require so much time. So then the users are motivated to estimate the process time just accurately or approximately. Now let us study the other CPU scheduling algorithm, which is non-preemptive, called priority scheduling algorithm. We say the shortest job first algorithm is a special case of this priority scheduling algorithm. So priority scheduling algorithm is a general case and shortest job first is the special case of it. Here, along with the processes and their CPU burst time, we have one more column called priority. So along with each process, a priority will be associated and the CPU is allocated to each process which has highest priority 1. Meaning, suppose at a time more than one process enter the system, then the one with the highest priority will get the CPU first. What happens if there are two processes having the same priority? At that time, first come first serve order will be applied. And also here we assume that the lowest priority one will be served at the end, and for that we give the highest number, and the highest priority one will get the lowest number. And also the process which is having the larger CPU burst will be given lower priority so that it will be executed at the end in order to minimize the average waiting time. And generally the priorities are indicated by some fixed range of numbers, like from 0 to 8, 9, like that, integer numbers, and always we assume that lower numbers represent highest priority. Now let us study this priority CPU scheduling algorithm with an example. Assume that we have the processes P1 to P5. Say the CPU time required by each process is like P1 requiring 10, P2 requiring 1, P3 2 units, P4 1 unit, P5 5 units. Now here in priority scheduling algorithm, along with these two columns, we have to consider one more column, priority. So here this is the pre-assigned priority for each process, and say the priority assigned to the processes is in this order, where P3 has priority 3, P2 1, P3 has 4, P4 has 5, and P5 has 2. And here the low number, meaning it has the highest priority. This is the assumption we have made in the beginning. So lowest number to which we have given means this has the highest priority. So it should be executed first. So when we represent it using Gantt chart, so which is the process we are serving first, which has the priority 1. This will be served first. So P2 for how many units? Time unit 1. Now among the rest, which is the lowest one? So we have to, next we have to serve P5. And P5 will be holding CPU for 5 time units. So after this 1 plus 5. So till 6th millisecond P5 execution will be done. Next we have to go for 3. So we have to start with execution of P1. P1 is requiring 10 time units of CPU. So 6 plus 10. So at 16th millisecond execution of P1 will be completed. So next priority is for P3. So next P3 will be taken up. P3 needed 2 time units. So 16 plus 2. At 18th millisecond execution of P3 will be over. Now the leftover and which has least priority is P4. So its execution will be taken up and will be completed at 19th millisecond. By these processes using priority scheduling algorithm. So average waiting time is the sum of the waiting time of all the processes divided by number of processes. So here the waiting time for P1 is 6. Waiting time for P2 is 0. Waiting time for P3 is 16. Waiting time for P4 is 18. For P5 waiting time is 1. So we will take the sum. Which is 41. Now average waiting time is 41 divided by 5. And it is coming with 8.2 milliseconds. Priorities are the numbers which are assigned to the processes earlier to the queue. So here the priorities can be assigned either internally or externally. Internally defined priorities, they use some measurable quantities or qualities like the time limits, they measure the memory requirements, and they take the count of how many files are opened, and also the ratio of average I/O burst to average CPU burst will be used to calculate the priority for the processes. Whereas while assigning the priorities to the processes externally, they are set by criteria outside the operating system, such as the importance of the process will be considered, the type and amount of funds being paid for the computer use that will be considered, and the department sponsoring the work and other things, they are coming into the picture while assigning priority externally. And here in priority scheduling algorithm, the major problem is indefinite blocking. It is also called starvation. What is meant by starvation? A process waiting for CPU indefinitely is called starvation. So this starvation problem can be overcome by using aging solution. Action. So aging is a technique used to solve the starvation problem. Starvation is a process waiting in the system for long time. Now how to do this aging solution? Suppose we have a process which has least priority. Then after some time we have to find out the priority of it, and we have to increase it to the next level so that it will come to one level up, and like that when it gets the highest priority it will be served. For example, if priorities range from 127 to 0, where 127 number process is having the lowest priority and the process with 0 number has highest priority, then we could increase the priority of a waiting process by 1 every 15 minutes. So eventually even a process with an initial priority of 127 would have the highest priority in the system. So when it comes to highest priority, it will be executed. Next, we will study the round robin CPU scheduling algorithm. We can say it is specially designed for time sharing system. So it is most suitable for time sharing systems. It is similar to first come first serve scheduling algorithm, but preemption is added to switch between the processes. So here a small unit of time called time quantum or time slice will be defined. A time quantum is generally from 10 milliseconds to 100 milliseconds. And in this algorithm, the ready queue is assumed to be a circular queue. The CPU scheduler, it goes around the ready queue, allocating CPU to each process only for a particular time interval, and when that time is over, then CPU is released from that process and given to the next process in the queue, and it will be done in a circular manner till the execution of all the processes are completed. To implement this round robin scheduling, we keep the ready queue as a first in first out queue of processes. New processes which enter the system, they are added to the tail of the ready queue. The CPU scheduler, it picks the first process from the ready queue, then sets a timer to interrupt after one time quantum and dispatches the process after that time is over. Now let us take an example for studying this round robin CPU scheduling algorithm, where the time quantum we will fix it to 4 milliseconds. And assume that the processes are P1, P2, P3, requiring the CPU burst time as 24 time units required by P1, 3 CPU time required by P2, 3 CPU time required by P3. And we have fixed the time quantum 4 milliseconds, and it is a round robin CPU scheduling algorithm. So here we will represent it using Gantt chart. Again, it is serving in the same way as that of first come first serve scheduling algorithm. So first it will take a P1, but instead of serving all the 24 time units, it will serve only for the first time quantum, which is 4. So when 4th millisecond is reached, then CPU will switch to next process. After 4th time unit, it will switch to P2. But the time required by P2 is within this time quantum. So it needs only 3 time units. So 4 plus 3 at 7th millisecond, P2 execution is over. So it will voluntarily releases CPU, and now CPU will be given to P3. Again, the time required by P3 is only 3 time units, which is less than the time quantum. So again it voluntarily releases the CPU. Next, it is treated as a circular queue. Our ready queue is a circular queue. So after completing P3, it will come back to P1 for next 4 time units. It will serve P1. Again, the completion of P1 is not over, the execution is not over. So it will continue the execution in the next time quantum also. So totally for how long P1 is executed? Here 4 time units, here 4 time units, here 4 time units. So totally 12. But here it needs 24 time units. So till then it will be serving only P1. Okay. So in the next time quantum also P1 will be served. 18 plus 4, 22, but still it is not over. We have 2 more time units. So here plus 2 units, P1 will be served. Okay, so 4 at 26th millisecond completion of P1 is done, but still one more session is required. So here the total completion will be at the end of 30th millisecond. So for P1 here, and then after that, since P2 and P3 are completed, then it will be serving P1 continuously till this 24 CPU burst time is completed. Now let us calculate the average waiting time for this round robin algorithm. Average waiting time, which is sum of the waiting times of all the processes over number of processes. So here the waiting time, first we will take a P1. For P1, what is the waiting time? See here, initially it will be assigned without making it to wait in the ready queue. So it is 0. But after that, there is a suspension of the execution of process P1, and it is again taken into consideration at time 10. So from 4 to 10, P1 has to wait. From time unit 4 to 10, P1 has to wait in the queue. So the next waiting time for P1 is 10 minus 4. So it is 6. Waiting time for P1 in the overall execution is 6 time units. Now waiting time for P2, which is 4. For P3, 7. See, now P2 and P3, they are waiting only for one time. Their execution is not repeated. So for that there is no further waiting time. Whereas for P1, there is a suspension and then re-execution has taken up. So there is a further waiting time. We have to consider that for P1. But for P2 and P3, only the initial waiting time. Now the sum of these three, which is 17, so average waiting time will be 17 by 3, which is 5.66 milliseconds. Here in round robin CPU scheduling algorithm, we met with two special cases. One is a process may have a CPU burst time less than the one-time quantum, or the other case is the process may have the CPU time more than the one-time quantum. Then how these two types of processes are executed? In the first case, wherein the CPU time is less than one-time quantum, then the process by itself will release the CPU voluntarily once the execution is over. The scheduler will then proceed to the next process in the ready queue. In the second case, wherein the CPU burst time is longer than one-time quantum, the timer, when it goes off, then the system will cause an interrupt to the operating system, and here a context switch will be executed and the process will be put to the tail of the ready queue and another process will be taken for execution. And this one which is put at the end of the ready queue will come in the circle again for the execution. So the CPU scheduler will select next process.